Physics Form 4, Chapter 5, Waves 5.2, Damping and Resonance. Damping. Do you know damping? What is damping? And what is resonance? Soon you'll find out. Damping and resonance for an oscillating and vibrating system. An oscillating system that is displaced and then left to oscillate without the action of external force will oscillate at its natural frequency. What happens to the amplitude of the oscillating system? Activity to observe the phenomenon of damping on an oscillating system. So here it is, the setup of the apparatus, the pendulum. Basically we have a string which we tied at retort stand, and the end we tied at whatever load that is, and then we're going to swing it left to right. Okay, left to right. Okay, we're going to displace it. How to begin it? How to begin the swing? We're going to displace it. Okay, we attract it to at this point at particular angle, and then we're going to release it. Then you know what will happen. It will going to swing, go back and forth like that. Okay. And then guess what? After several times, what will happen to the swing? What will happen? Oh yeah, before that, this is what we call, from this distance to this point, is what we call amplitude, with a symbol of capital A, amplitude. Okay, after several times, what will happen to this amplitude? Let's say the amplitude we begin with 50 centimeter, okay, and then we got another 50 centimeter to the right side, and it keeps swing back and forth like that. And after several times, what will you guess happen to this amplitude? What will happen is what we are try to find out in this subtopic. Okay, everyone, let's get back to work. So the idea is you'll see that this amplitude keep decreasing over time, and eventually it will come to stop. Okay, and stop at there. So the amplitude will decrease over time. Figure below shows the graph of displacement against time for the oscillation in activity above. So here it is, we got a graph. Displacement Refer to what? Refer to amplitude. Refer to amplitude. Okay, and versus time. Okay, if you notice, if we graph what happened here, so it will look like this. So if you notice, there is something that you already know. There is something that different, and there is something that remain the same. What is it? What is it that remain the same? And what is it that changing? What is it? The things that change is amplitude. As you can see, the amplitude decrease. But there is one thing that never change, and what that is? Do you notice? There is something that never change. That it is the time, the time taken. So you see, from this point to this point, it is the same time as this point to this point, this to this, this to this, this to this, and so on. Okay, so you see the time never change. The only thing that change is the amplitude. So that is what damping means. Damping. When damping happen to any kind of vibration, any kind of oscillation. Okay, means that you should be able to imagine that only amplitude decrease, but not the time. Okay, it doesn't the damping doesn't bother the time. The next question that you should ask is, what caused this damping? What caused this damping? Let us read this. The oscillation of a simple pendulum experience significant external damping, but insignificant internal damping. Insignificant internal damping. For the vibration of a spring, both external and internal damping happen significantly. Okay, I don't know either you understand this or not. Soon you'll find out. Observe that the amplitude for the oscillation decreases with time. Figure below shows the graph of amplitude against time for the oscillation of the simple pendulum. Okay, amplitude decreases with time. Periodic force is a force which acts at specific time interval. Periodic force does not act continuously. An oscillation with its amplitude decreasing with time shows that the system experiences a gradual loss of energy. And here it is. Here it is the cause of the damping. The loss of energy. The loss of energy is the reason why damping happen. Finally, the oscillation stops. This phenomenon is known as damping. oscillating systems experience loss of energy due to actually how you may ask more detail. You may ask again, then what caused the system lost the energy? Okay, there are two things happen that make any system lost the energy. First, the first thing is external damping. External, internal, the external. What is external damping? Oscillating system lose energy to overcome friction or air resistance. So here it is what causes external damping, because these external things, that is air friction that come from air resistance, friction that come from air resistance. Okay, now internal damping, oscillating system lose energy because of the stretching and compression, compression of the vibrating particles in the system. Do you know stretching and compression? Now let's say I have this one of the system, one of the oscillating system that I can make only by this simple tool. So here it is. I got this plasticine as a load attached to the end of the ruler. So the ruler here is represent as the string. So I'm going to do is I'm going to oscillate the ruler like this. First it doesn't move like this. It at rest. In order to make it move, in order to make it swing, we're going to displace it. Okay, a little longer like that, and then we're going to release it. Okay, so you'll see it start to oscillate like that. Okay, so you'll see the amplitude become decrease over time. Okay, and what caused this damping is because you know that up here and below here is what is it got air all the way, all of its motion up and down. So this thing collides with air surrounding it. That's what make the that's where the friction comes from air resistance. Okay, and not only that, not only this external force that is air resistant, but also this internal force that coming from this string here, this ruler here, compress. Okay, what happened up there in this position? What happened up there? It is stretching. It is stretching. Here it is stretching. Okay, the molecule stretch up there. The molecule resists this motion. They stretch to take this motion back to its original position like this. Okay, and at the same time, what happened under there is the what? The compression. Okay, compression took the place. compression. So this compress do what? It try to pull back, all the molecule to back to their original state. Okay. Moving along, damping is the reduction in amplitude. Do you know reduction? Means decrease in amplitude in an oscillating system due to loss of energy. During damping, the oscillating frequency remains constant. So you see, there are things that change, there are things that doesn't change. That is frequency. Frequency doesn't change. Time to oscillate doesn't change. Okay. Remains constant while the oscillating amplitude decreases. The effect of damping can be overcome by applying. Okay, how to overcome the damping? Simple. By applying periodic external force on the oscillating system. The periodic external force transfers energy into the oscillating system to replace the energy lost. The system is said to be in a forced oscillation. The system is said to be in forced. Okay. Means we when things oscillate, we don't want the amplitude decrease, so we apply the force continuously, and also periodically. If you understand what does this mean, periodically, means a good timing lah. Okay, a good timing. We don't apply force not in a good timing. Okay. When a periodic force is applied to an oscillating system at its natural frequency, the oscillating system is said to be at resonance. Now you come to know the second things that you supposed to know. Before you know, you need to know about damping, and now you do know about resonance. So during resonance, system oscillates with its natural frequency. Point number 2, system oscillates with maximum amplitude. Okay, this is what happened when the oscillation is in resonant. It's resonant. So here it is. What will happen to the system? Okay. It got natural frequency and it will maintain the amplitude. It will maintain the amplitude. So take this moment to read this activity to study the production of resonance using tuning fork, kick, and buttons pendulum. Okay, to study the production of resonance. So this activity, soon you'll find out what does it mean by resonant? So can I leave you 5 minutes uh, to read this activity? Okay, you need a moment with something to read. Take your time. Okay, back to this. So in order to maintain the amplitude, what I supposed to do? So the amplitude will remain at a maximum amplitude. I need to apply some force, okay, to the system. Okay. So this my finger here. I can push this, but I must do at certain time, at certain phase, a good timing. I cannot push when it come to me. I cannot push when it come to me. If I push it, it will not help it to increase the amplitude, but the opposite way, it will decrease. It come to me, I push it. It come to me, I push it. No. When it come to me, okay, and then when it's about to leave me, then it is time I push it. Like that. Okay. And then the amplitude keep increase back to its maximum amplitude, and then it will come back, swing back to me. Okay. When it come to me, then I don't push it. I don't push it. And about it going to leave me, then it is a good time to push it back, like that. So maybe you can see things clearly under this camera. This camera got on the a lower bit rate, a lower frequency, but I believe you got the idea lah. That is what meant by periodic force. Okay, a good timing lah, a periodic force. So in order to prove to you that the resonance exists, we can there is a production of resonance. So here it is two simple things that we can do by using tuning fork. I believe you know about this tuning fork. You have learned at lower form in science, I believe. So what we do with this tuning fork? We can vibrate it, and then we place it close to our ear, and we can kind of hear the sound, the sound of vibration. Okay, so the idea is, if we got these two tuning fork, we place it close like this, but notice we must have a little gap there, so they don't touch each other. So what we're going to do, we're going to hit this tuning fork number one, P, tuning fork P. We hit this, and then you're going to observe if something happen at this tuning fork Q once you hit this, and what that observation that you will make for this tuning fork Q. you'll see that the tuning fork Q also vibrate as this vibrates. It kind of try to follow this to vibrate. Why is that happen? Why is that happen? So here we have buttons pendulum. Is what they call it. Buttons. You need to memorize this. Button is the name of a person who found this. Okay. Buttons pendulum. The name of the scientist. Buttons pendulum. So also the simple activity. We need a string up there, and then we're going to have several pendulums tied to the string. Okay. If you notice, all the pendulums is different in length. So the idea is different the length, different the frequency. Okay, this is how we set the frequency of the pendulum is by we set the length of the pendulum. Okay. How to make it? Can you imagine how to make it the pendulum go faster? Is it when we use short string or long string? Which one going to oscillate faster? Is it short string or is it pendulum A or pendulum D? If you oscillate them A and D simultaneously, okay, then which one you going to see that the pendulum going to move faster, oscillate faster, go forth and back like that? Which one? Is it pendulum A or pendulum D? Is it pendulum A or pendulum B? Under this camera, I cannot show you the pendulum, but I can show you something similar. Okay, something similar. Also the same thing here. Do you understand what I'm asking you? Is it okay? So this represent pendulum A. Why? Because short string. Short pendulum. So here it is. How to represent that? This my right hand here. I grab it there. Grab the ruler there. Okay, so you'll see the speed. Oh yeah, you know what? This camera it's not good. It got lower frequency lah. That's why you can never see the real time. It's vibrate. Okay. And this, if I make it long like this, I grab it here. So the idea is the pendulum is longer. So how will it oscillate in terms of period? Go back and forth like that. If you notice, it take a little longer time, correct? The longer the pendulum, the longer that it takes to start from this point until it go and then back to the same point. It take longer. So if I make it short, you'll see it go back and it go forth and back with a high speed. So it doesn't require a long time to do the oscillate. You got the idea? I believe you do. So that is the idea, how to adjust the period period of oscillation is by adjusting the length of pendulum. Okay, never mind that we come to this business, Barton's pendulum. The purpose of these activities is to what? To show to you that the only system which has same frequency can work. Okay, means that can catch the energy and then make its amplitude to go maximum. The only system that have same frequency, remember that key. So here we got extra pendulum which called X. Okay, if you notice, this X is about same length as what pendulum? As what pendulum? A, B, C, and D. This the length of this pendulum X the same as the length of which pendulum? Is C, correct? They are about at the same size of length. Okay, means that this X means that this C got the same frequency, the same frequency as this frequency of X. Why? Because they both have the same length. Okay, remember what I told you? The only thing that can catch the energy and use the energy to bring the amplitude to maximum is the one that has the same frequency, okay, as the other system. So the idea is we're going to oscillate this X. Okay, we're going to displace this X. Okay, and then give it a little time. We will observe between this A, B, C, and D who able to follow this X. And guess what? Who going to follow this X with maximum that it can go, maximum amplitude. Okay, and you'll see that C will also try to match this motion, try to oscillate. So they will oscillate together like this, back and forth with maximum amplitude, while the other also trying to match with the motion, but they cannot. Okay, it is like they struggle to copy the motion, but they cannot. Why? Because they got different frequency. That is the idea. So it's why they cannot match the motion of this X. Oh yeah, before that, this tuning fork Q also can match this motion. Why? Because this tuning fork also is got the same frequency as this tuning fork. Mean their height is the same. Their height is the same, which represent the frequency. Okay, then this is why tuning fork able to follow tuning fork P to oscillate with the highest amplitude that it can go. The vibrations of tuning fork P have forced tuning fork Q to vibrate in resonance with P. Okay, so a good way to say things, you need to use this key. When you come to explain, you should be able to use this key. What force what? What system force what system? Usually, what system is the one that oscillate at the moment. And force what system? Usually, the system that being forced is the system that is at rest. Okay. To vibrate in resonance with P, in resonance. A key number 2 that you need to use, that is resonance. Vibrate in resonance. Okay. Resonance means, what is resonance means? Resonance means it can follow the it got natural, they both got natural frequency. The natural frequency of the system that try to follow something is the same as the natural frequency of the system that they want to follow. And number 2 is, what resonance means is, when they both have a natural frequency, then the one that try to follow can do the maximum amplitude, can absorb the energy from system 1, and then can use the energy to maximize the amplitude. Is what resonance means. Energy is transferred from tuning fork P to tuning fork Q. Okay, energy is transferred. Otherwise, how can they do the work to oscillate? First, need energy to be transferred before they can work. Tuning fork Q vibrates with maximum amplitude and produces sound that can be detected. Okay, the oscillation of, now come to explanation of this Button's pendulum. The oscillation of brass pendulum X transfers energy to pendulums A, B, C, and D. So this oscillation of this X kinda transfer the energy through this what? Now you know what is the purpose of this string up there. Okay, is in order to transfer the energy from this pendulum, it's going to transfer the energy to all the string up here, and then from the string up here transfer the energy back to every pendulum that tied to him. Okay, so it is fair, everyone got the same energy, because they all been tied at the to the same string up there. But what? But none of them can match the motion. But except the only one who got the same frequency, which in this case is the same length, can match the motion. The oscillation of brass pendulum X transfers energy to pendulum A, B, C, and D, causing all pendulums to oscillate. Okay, actually all pendulums try to oscillate lah. Resonance happens to pendulum C. Okay, maximum resonant, all of them, the only one can do the maximum amplitude, is the only one who got the same natural frequency as the oscillate system. Okay, as the given oscillate system. Happens to pendulum C only because pendulum C has the same natural frequency as pendulum X. Pendulum C oscillates with the largest amplitude, while the other oscillate with not so good in amplitude. Effects of resonance in daily life. Okay, so here is a good video to show to you lah. Okay, of how this resonance really important for us to know, to study in our life. Okay, because if we don't care about it, our life will not going smooth as we suppose it to be. So here it is, what happen if we don't care about resonance. I'll try to scan this. You're going to see something special happen. You see what happened? It is very weird, right? How can this bridge, which is a very very heavy tones heavy, it is, but it can vibrate like this. Doesn't this weird? This is the mistake that made by the engineer, the architect at that time. They doesn't count for resonance, and this is what happened. So what caused this to oscillate like that? What caused this bridge to oscillate like that? Do you know what caused this bridge to oscillate like this? Okay, siapa nak naik jambatan ni? It's very interesting. and the last thing happened, collapse. The bridge collapsed. Okay, I believe you got the idea. So what caused this bridge to oscillate like that? Is the air, sorry, the wind, the wind, okay, the wind, the moving of air is what we call the wind, the wind, the frequency, the natural frequency of the wind that blow the bridge is the same frequency, the same natural frequency of the bridge itself. This is why the bridge can match, try to follow the motion of air and get its amplitude to maximum before it broke and fall down. That is what happened. So so it is a big things, resonance we need to study it, so it won't bother our life. And we got many more lah. Okay, the London Millennium Footbridge was opened and blah blah blah, and then the bridge oscillate. Okay, happened in June 2000. Okay, June 2000. This one, the one that you seen on the video is happened in 1940. And the bridge is, the name of the bridge is Tacoma Narrows in Washington, USA. And this one is London Millennium Footbridge. And this one is resonance is used in the tuning of musical instruments. This too is a phenomenon. Sorry. This too is phenomenon. This too is phenomenon. While this one is the application. The phenomenon is God made. Okay, God made. The application is man-made. Okay, man-made. Okay, that also come from God lah. So you might not your faith is straightforward. Formative practice. Now we have come to an end. Okay, let's end this subtopic with this practice. Formative practice 5.2. Number 1, what is the meaning of damping? What is the meaning of damping? Remember what I told you? For all the definition, you're supposed to do what? You're supposed to collect them, okay, and put it on, write it down on some book lah. Okay, so here it is. What damping means? Where is it? Sorry, here it is. What damping mean? Under here, damping is the reduction in amplitude in an oscillating system due to loss of energy. So you should write this down somewhere. Try to collect all the definition. So damping, here it is, we got more definition, more detail. External damping, what it is, internal damping, and what it is, the definition. Should collect all of them. Number 2, sketch a graph of displacement against time for a system experiencing damping. You should learn how to sketch a graph of damping or any kind of graph. Any kind of graph. Here I try to demonstrate to you how you're supposed to do. Here you're going to put the label displacement. Okay. You're going to draw the two axes. Okay, and this represent what? Time. Time. So before we able to sketch the damping waves, let's have this. Let's have this scale. Let's have this interval. Okay, the same interval like this. So it will help your the way you sketch. And then before that, also the thing that the guideline that you need to have is like this. You're going to make the line which is become swallow over time like that. Okay, just have a okay, just like that, simple one. Just a guideline. So you'll see they will begin with amplitude. It will begin with amplitude with maximum amplitude. Okay, this is the first time you displace things before it start to swing. Okay, it's going to look like this. So here it is, point number 1 that we have. So now you need to practice lah. So this you try to make this go in the middle, of the scale. So these two every time in the middle of the scale, back to the middle, go up, back in the middle, go up. Okay, see, this is when you show the amplitude decrease. Okay, while the time taken remain the same. It doesn't affect the time to oscillate. Okay, it doesn't affect the time, means it doesn't affect the frequency lah. Okay, it doesn't affect the frequency. The frequency remain the same. That's how to answer question number 2. Also, the thing that you need to mention is T. T, 2T, 3T, and then you need to mention the okay, you're going to have this arrow like this to show that the amplitude decrease. Then you will have full mark for this lah. Okay, because of the complete label that you make. Number 3, state 3 example of the effects of resonance in our daily life. State 3 examples of the effects of resonance in our daily lives. The effect. And what is it? it is the, you can use this lah, the Tacoma what? The Tacoma Bridge collapse. Okay, collapse. And then London Millennium Footbridge collapse. Okay, and then what? In our in our daily life, am I mistake something? Effect of resonance in our daily life. Daily life. Our, not their, our. Which is wrong to give that example. What is the, how to answer this question? Resonance. Do you have any example of resonance happen in our daily life? And what is it? Example like what? Like what? Like what? Oh yeah, it is like you. It is like when there is jet. Okay, when there is jet passing through our roof, our house, then we'll find out the things, some of the thing in our house will vibrate in high amplitude, and maybe if you're lucky enough, not lucky enough, the things will broke down. Example, the glass, the glass of window, the glass of window. So this is why they prevent any jet to flying through up our residential, because they know that some of the object underground got the same frequency, got the same natural frequency as the sound of the jet, you know. Means that it can catch it can absorb the energy, and then it can make themselves oscillate with high amplitude, you know, maximum amplitude, and that what will make the things broke. Okay, the things broke. Okay, that is the example of resonance in our daily life. Other than this is, if you know, do you know soprano? Is it soprano? The one who can is it sing? The one who can sing with high pitch, and if he or she able to match the frequency of his pitch with the frequency of the glass, a drink glass, let's say, you know what, the glass will broke. The glass will broke because of the same natural frequency. Then the glass will start to oscillate or vibrate with high amplitude. That eventually will make the glass broke lah. Okay. Other than that, is it the earthquake? How about earthquake? Do you know earthquake? Earthquake. So here earthquake too is the effect of resonance. So we have this earthquake, which the soil, the underground going to go like this, up and down like this. Okay, and there will be whatever the things that stand on the ground like that. So some of them they will collapse, some of them they will not collapse. Why? Some of them will collapse, some of them will not collapse. Okay, why? This collapse first. Why? So you see, which one is taller? The red one or the blue one? The blue one is taller, correct? But sometimes, you know what? Sometimes when there is earthquake, they see that the building that collapse is not the taller one, but the not the taller one, the lower one. Hey, how to say that? The taller. What is opposite taller? Taller. What is the opposite for taller? Huh? Somebody? Huh? I don't hear it clearly. Taller and smaller. Cannot say smaller. Smaller means all the shape is smaller. No.
Short.
The short. Can use lah the short. The short one. Collapse. The shorter one collapse. But not the taller one. Hey, why? Why is that? Doesn't it weird? This is what you think all of the time, correct? If there is an earthquake, the only thing that will fall easily is the taller one, correct? Well, you are wrong. The thing that will fall down is the building which has the natural frequency as the same as the earthquake, the natural frequency of the earthquake, you know. Okay, then that one will collapse first, will fall down first. So this is the idea that this is the idea of the architects nowadays. They know about this resonance. So this is when they have measured already how the building they going to build, how tall the building that they are going to build. Okay, they must build the building which has natural frequency not equal to the frequency of the earthquake. So soon the building, if there is earthquake happen, the building will not be able to absorb. It try to absorb energy, but it cannot follow. It cannot follow the earthquake. It cannot follow vibrate. Why? Because the frequency is not the same. That is the idea. Do you understand me? Now, come to number 4. How can resonance overcome damping of an oscillating system? How can resonance overcome damping of an oscillating system? Okay, you know how to explain this lah. Okay, first is what? First is okay, you explain this. You use this explanation. When a periodic force is applied to an oscillating system at its natural frequency, the oscillating system, okay, you go to this word. System oscillate with its natural frequency, and then system oscillate with maximum amplitude. That's all. is how to answer question number 4. Okay? Any question? Any question? Are you okay? Okay. Okay, we have come to the end. If you got no question, then are you sure you got no question?
Yes, sir.
Yes, sir.